Hi, this is Siddharth from VLSI Facts. Today, in the third lecture of the lecture series on digital electronics, we would learn about conversion of number systems. In the last lecture, we have studied about the representation of four number systems. These are decimal, binary, octal, and hexadecimal. In this lecture, we would learn the conversion of each number system to other among these four number systems. Let us discuss how to convert any number system to its decimal form. The technique is multiply each bit by x to the power n, where x is the base and n is the weight of the bit. Then add all the results to get the final decimal number. Let us solve some examples. We will start with the first example, which is a binary number, that is 101011. Now we will convert this to its corresponding decimal number. So what we will do, we will multiply each bit with 2 to the power n, where n is the weight of that particular bit. So if you will count, this is 1 2 3 4 5 6. So we will start with the LSB, that is 1 into 2 to the power 5 plus 0 into 2 to the power 4 plus 1 into 2 to the power 3 plus 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. So this will be 32 plus 0 plus 8 plus 0 plus 2 plus 1. So it will be 43 in decimal number system. Okay. Now we will convert a octal number to its corresponding decimal number. The number is 724 in octal number system. So as we have done in the previous example, here also we'll multiply each bit with 8 to the power n, where n is the weight of the number or position of the number. So here there are 3 digits, so the MSB's position is 2. So 7 into 8 square plus 2 into 8 to the power 1 plus 4 into 8 to the power 0. So this is 7 into 64 plus 2 into 8 plus 4 into 1, which is 448 plus 16 plus 4, which is equal to 468 in decimal number. Now we will convert a hexadecimal number to its corresponding decimal form. This number has also 3 digits. So a into 16 square plus b into 16 to the power 1 plus c into 16 to the power 0. Now in hexadecimal, a is 10, b is 11, c is 12. So we can write 10 into 256, 11 into 16 plus 12 into 1. This is equal to 2560 plus 176 plus 12, which is 2748 in decimal. Now we will discuss how to convert a decimal number to its binary form. The technique is divide the number by 2 and keep track of the remainders. Repeat the process till the quotient becomes 0. Now let us solve one example to understand the process. The decimal number given here is 125, and we will convert this particular decimal number to its equivalent binary form. Now to perform this, we will keep on dividing the number 125 with 2, and we will keep track of the remainders. 125, we will divide it by 2. This will give us 62, and remainder is 1. Divided by 2, 31. Remainder is 0. 15, 1, 7, 1, 3, remainder is 1, 2, remainder is 1, and finally dividing the 1 by 2, quotient is 0, and the final remainder is 1. Now you will collect these reminders from bottom to top, or in other words, the bottom bits will be MSB and the top bit will be LSB. So this is MSB, this is LSB. Then it will become 1 1 1 1 1 0 1. So the decimal number 125, its equivalent binary number is 1111101. Here we will learn how to convert an octal number or a hexadecimal number to binary. The conversion procedure is almost same for both octal and hexadecimal. Let us see how it can be done. The technique is, in case of octal to binary conversion, convert each octal digit to a 3-bit equivalent binary representation. Similarly, in case of hexadecimal to binary conversion, convert each hexadecimal digit to a 4-bit equivalent binary representation. Now just for your information, each octal bit should be represented by a 3-bit binary because 8 is equal to 2 to the power 3. Similarly, for a hexadecimal number, each digit of hexadecimal number should be represented by 4 bits of binary because 16 is equal to 2 to the power 4. Now let us solve some examples to see the process how to convert a octal to binary and hexadecimal to binary. We'll start with the first one, which is a octal number, that is 705 in base 8. Now we will convert it to its binary equivalent form. Let me to divide this so that it will be easier to write. Now this 7, if I will write in its equivalent binary form of this particular digit 7, then it will be 1 1 1, 0 is 0 0 0, 5 is 1 0 1. Now I will just concatenate the binary equivalent of all these 3 digits to get my final binary number. So the final number will be 1 1 1 0 0 0 1 0 1 in base 2. Now let us solve a hexadecimal number to binary conversion. The number is 10AF in 16 base. Now we will convert this number to its equivalent binary number. Now in the similar procedure, what we will do, we will write the equivalent binary number of each digit and then concatenate them. So if I will write this number 10AF and write the equivalent binary number of each digit in 4 binary bits. So 1 will be 0 0 0 1, 0 will be 0 0 0 0, A will be 1 0 1 0, F will be 1 1 1 1. Now this 3 leftmost 0 can be discarded. So the final number will be 1 0 0 0 0, 1 0 1 0, 1 1 1 1. Now this is the final binary number. Now we will see how to convert a decimal number to its octal equivalent or hexadecimal equivalent. The technique is, for octal conversion, divide the number by 8. For hexadecimal conversion, divide the number by 16. And in both the cases, keep track of the remainder till the quotient comes to 0. First, we will solve an octal conversion example. Now the given number is 1234 in base 10. Now we will convert this particular number to its equivalent octal number. So I will keep on dividing this number with 8. The quotient will be 154, remainder will be 2, 19, remainder is 2, quotient is 2, remainder is 3, and now finally the quotient is 0 and remainder is 2. Now we will collect all the reminders from bottom to top. That means this will be LSB and this will be MSB. So the equivalent octal number of 1234 will be equal to 2322 in base 8. Now let us convert the same decimal number to its hexadecimal equivalent. So we will start the similar division process. Here we will divide the number with 16. So here the quotient will be 77, remainder will be 2. Quotient is 4, remainder is 13. Finally, quotient is 0, remainder is 4. Now again we will collect these numbers from bottom to top. In hexadecimal, 13 is written by D. So the final hexadecimal number will be 4D2 in base 16. So in summary, whenever we will convert a decimal number to any number system, the technique is divide the number by x. The way we have divided here, for finding the octal number, we divided the number by 8, and to find the equivalent hexadecimal number, we kept on dividing the number by 16. So whatever be the base, any number system you want to convert the decimal number, so take the base of that particular number system and divide the decimal number by that base value. Then keep track of the remainder as we have done over here. And finally collect all the remainders from bottom to top to get the final result in the desired number system. Here we would discuss how to convert a binary number to its equivalent octal or hexadecimal number. Both the conversion process are fairly similar. The technique is, for octal conversion, group bits in threes starting from right, append zeros to the leftmost bits if required, then convert those grouped bits to octal digits. Similarly, for hexadecimal conversion, group bits in fours starting from right, append zeros to the leftmost bits if required, and finally convert those grouped bits into its corresponding hexadecimal digits. Let us discuss examples from both the types. First one is a binary to octal conversion. Here the binary number is 1011010111. Now we will convert this particular binary number to its equivalent octal number. Now we will group the binary bits into 3 bits group starting from the right. So we will group the number into 3 bits, and in this last number, which is the MSB, since we are left with only 1 bits, we will append 0 to make it a 3-bit group. Now we will replace all these grouped bits into its equivalent octal number. So 111 is 7, 010 is 2, 011 is 3, and 001 is 1. So the equivalent octal number of this particular binary number is 1327 in base 8. Now let us go for a binary to hexadecimal conversion. The binary number given here is 1010111011. Now to find the equivalent hexadecimal number, we will group the bits starting from right, and we will group them into 4 bits. So this is one group, this is one group. For the MSBs, we will append 2 more zeros to have 4-bit group. So now converting these group of bits to its equivalent hexadecimal number, this one will be 2, this is 1011 is B, again 1011 is B. So the equivalent hexadecimal number is 2BB in base 16. Now we will learn how to convert an octal number to hexadecimal or vice versa. These conversion processes are very simple. We just need to use binary as an intermediary. Let us solve one example from both the conversion. The first one is a octal number, that is 1076. We will convert it to its corresponding hexadecimal number. Now first we will convert this number to its equivalent binary, and to do that we will write each digit of the octal number in the 3-bit binary form. So 1 can be written as 001, 0 will be 000, 7 will be 111, and 6 will be 110. Now this is a binary number. To get the final hexadecimal number, we will group 4 bits starting from right, since 16 is 2 to the power 4 as we have discussed earlier. Now the first 4-bit group is 2, the second one is 3, and the third 4-bit group is E. So the equivalent hexadecimal number of 1076 in base 8 will be equal to 23E in base 16. Now we will discuss one example where we will convert a hexadecimal number to its equivalent octal number. The example is 1F0C in hexadecimal number. We will find out the corresponding octal number. Now for this, again we will convert this hexadecimal number to its corresponding binary number. So to do that, 1 can be written as 0001. Here we have converted each digit of the hexadecimal number to a 4-bit binary number. Then F can be written as 1111. 0 is 0000. C is 1100. To convert this binary number to its octal form, we will group them into 3 bits each. Now the last 0 can be discarded. Now this is 1, this is 7, this is 4, this is 1, this is 4. So the final octal number is 17414. Now we will discuss an important concept of number system conversion, that is the conversion of fractions. Till now we have learned about different number system conversion, but for the whole numbers only. Now you will learn number system conversions for fractions. First of all, we will learn how to convert a binary number, which is a fraction binary number, to its corresponding decimal equivalent. Let us understand the process through an example. The given fraction binary number is 10.1011. Now we will convert this to its corresponding decimal number. To perform the conversion, what we will do, we will multiply each bit of this binary number with 2 to the power n, where n is the weight of that particular bit. So this will be 1 into 2 to the power 1 plus 0 into 2 to the power 0 plus 1 into 2 to the power minus 1. Now this particular one, the position of this particular one is minus 1, or the weight of this particular one is minus 1, weight of this particular 0 is minus 2, the weight is minus 3, and the weight is minus 4 over here. So 0 into 2 to the power minus 2 plus 1 into 2 to the power minus 3 plus 1 into 2 to the power minus 4. Now this will be 2 plus 0.5 plus 0.125 plus 0.0625. Now totaling this number, we will get 2.6875 in its decimal form. So in summary, the technique is to multiply all the bits with 2 to the power n, where n is the weight of the bit position. Do it for both before and after the decimal point. Now we will learn how to convert a fractioned decimal number to its corresponding binary number. Let us consider an example to understand the process. The given example is 6.25 in its decimal form. Now you have to convert this particular number to its corresponding binary number. Now to do this conversion, we will consider the part which is before the decimal point separately and the part which is after the decimal point separately. So we will start with the bits before the decimal point, which is 6. Now to get the equivalent binary number of 6, we will perform the repeated division process, where we will keep on collecting the remainder. So here the remainder is 0, remainder is 1, remainder is 1. So this is what the equivalent binary of 6, that is 110. Now I will consider the bits after the decimal point, which is 0.25. Now to find the equivalent binary number, I will keep on multiplying this number with 2 and keep on collecting the whole number before the decimal points. So if I will multiply this number with 2, this will be 05.0. Now I will collect this one. Now again multiply this number with 2. So this will be 0.1. Now I will collect this one. Now I will collect them from top to bottom. That means this will be MSB after the decimal, and this will be LSB after the decimal point. So I can write that 0.25 in decimal is equal to 0.01 in binary. So the binary equivalent of decimal number 6.25 will be 110.01 in binary. So in summary, for the number before the decimal point, we will follow the same technique which we have followed for the whole number conversion. That means repeated division process and collecting the remainder. Now for the number after the decimal point, we will multiply it with 2, collect the whole number part, repeat the process till the fraction part will become 0. To understand the process, let us consider another example. Okay, the given example is 3.14579 in decimal number, and we are trying to figure out the equivalent binary number. Now for the digit before the decimal point, that is 3 over here, this is simple as we have discussed earlier. Keep on dividing 3 by 2 and keep on collecting the remainder. We will go from bottom to top. So I can write 3 in decimal number, the equivalent binary number is 1 1. Now the most important part comes where we will find the equivalent binary number of the fraction part, that is 0.14579. Now as we have performed in the previous example, we will keep on multiplying this number with 2 and keep on collecting the whole number part. So this will be 85192. Collect this 0, again multiply this with 2, this will be 61385. Collect this number 0, 0.58316. Multiply this with 2, this will be 1.16632. Collect this one. Now since this one is collected, now we will multiply 2 with 0.16632. That means we will only multiply 2 with the fraction part, not with the whole number part. And this will be 0.3326. This 0 will be collected. Multiply this with 2. This will be 0.66528. Collect this 0. Multiply this with 2. This will be 1.33056. Collect this one. Now I will multiply 0.33056 with 2. I will get 0.66112. Collect this 0. Again I will multiply with 2. So I will get 1.32224. Collect this one. Now the question is, till what point we will keep on doing this multiplication. As in the previous example, we have seen that when the fractional part becomes 0, we stop the process. But in this case, it looks like we will never reach to 0, or we will reach to 0 after so many multiplications. So we cannot keep on doing this. So whenever you face this type of scenario, you perform this multiplication for at least 5 bits and then you can leave it. So here we have done enough number of multiplication. So we'll stop it here and we will group the collected bits starting from the top one till the bottom one. 0.14579 in decimal, that will be equal to 0.001000101, and it can still continue in binary number. Complete conversion of 3.14579 in decimal to its binary form can be written as 11.001000101 in its binary form. Now here we will see how to convert a fractional binary to its equivalent octal and hexadecimal number. We will consider two examples to understand the process. The first one is a binary to octal conversion. Here the binary number is 10.1011. Now to convert this number to its equivalent octal number, we will again consider the digits before the decimal point separately and the digits after the decimal point separately. Now again in this case we will group the bits into 3 bits each. Now before the decimal point we have only 2 bits, so we will append a 0 and group them, and after the decimal point we have 4 bits, so we will group them into 3 bits. Finally we find a single bit remained, that is 1, so to make it a 3-bit group we will append 00 after it. So now if we will write down the equivalent octal number of these 3-bit groups, this will be 2, this will be 5, this will be 4. So the equivalent octal number will be 2.54. Now in another example we will see how to convert a binary fraction number to its equivalent hexadecimal number. Here we will group the bits into 4 binary bits to get its equivalent hexadecimal number. So the bits before the decimal points we have only 2 bits, so we will append 2 more zeros over here, and after the decimal point we have 4 bits. So the number before the decimal point, if we will convert it to its equivalent hexadecimal number, this will be 2, and the number after the decimal point, if we will convert the grouped 4-bit numbers into its hexadecimal number, this will be b. So the equivalent hexadecimal number of 10.1011 in base 2 will be 2.b in its hexadecimal form. That's all for this lecture. In this lecture, we have discussed about conversion of different number systems. If you feel that you need more detailed lecture on number system conversion for fractions, then do drop your message in the comment section. I will prepare and upload a more detailed video on it. In the next lecture, we will discuss on the signed numbers. Hope you have liked the lecture video. If you have any doubt or you want to give your opinion regarding this lecture, please write it in the comment section. If you feel that this video will help any of your friend, then do share this video with them. If you want to watch the other videos in this lecture series, then subscribe to the channel and don't forget to press the bell icon for the notifications. Thank you for watching the video. We will meet in the next lecture. Bye bye till then. Take care.